Deep under the border between France and Switzerland, a few atoms are floating inside a trap, pinned in place by magnetic fields, held in a chamber emptier than the space between the stars. They are not ordinary atoms. They are antimatter, the exact opposite of everything you were made of. And the people who built them cannot let them touch the walls. One brush against ordinary matter and they are gone. In a small pulse of pure light. That is the quiet horror of the place. The laws that wrote our universe say the whole sky should be made of nothing but that light. Equal parts matter and its twin, born together, erasing each other, leaving a bright and empty nothing. Instead, there are stars. There is a planet under your feet. There is you. Something tipped the balance, barely, and no one down there can say what. The closer they look, the worse it gets. Run your eye along a flat stretch of farmland near Geneva, and you would never guess it is there. A ring sits beneath the soil, hundreds of feet down, crossing back and forth under the border between France and Switzerland. It is about 17 miles around, one long tunnel bent into a perfect circle. Inside, it is colder than the empty space between the stars, and emptier than that space too. This is the largest machine human beings have ever built. The people who run it call it the Collider, though its full name is the Large Hadron Collider. It does one thing, over and over, with terrible precision. It takes the smallest pieces of ordinary matter, the protons at the heart of every atom, and it throws them at each other almost as fast as light can move. To do that, it has to fight the universe a little. Protons hate being crowded together, so the machine strips them out of hydrogen gas, herds them into tight bunches, and sends two streams racing around the ring in opposite directions. Thousands of magnets, chilled to a degree or two above the coldest temperature there is, bend the beams and hold them on the line. By the time the protons are at full speed, each bunch laps the 17 miles more than 10,000 times every second. Then, the machine lets them meet. At 4 points around the ring, the two beams cross and a handful of protons slam head-on. For an instant, the energy of that crash packs into a space smaller than a single atom, and the temperature there climbs past anything else in the known universe, hotter than the core of the sun, hotter than a supernova. For a sliver of a second, in that tiny spot, the conditions look the way the whole universe looked a fraction of a second after it began. That is the real reason the machine exists. It is not built to break things. It is built to go back, to recreate the first heat, the moment when everything that is now a galaxy or a planet or a person was nothing but raw energy with no shape yet. And at each of those crossing points sits a detector the size of a cathedral, wrapped around the beam in layers, watching. When the protons collide, the energy does not just scatter, it turns into matter. New particles spray outward, born from the crash, and the detectors record every track. This is the part that should feel like a triumph, and for a long time it did, because the machine showed us something we expected. When pure energy turns into matter, it never makes matter alone. It always makes a partner alongside it. For every particle that appears in the wreckage of a collision, an opposite particle appears with it, born in the same instant, carrying the same mass and the reverse charge. Two things, made together, out of nothing but heat. The collider does this every time. It is one of the most reliable facts in all of physics. Energy becomes a pair. Never one, always two, balanced, equal, opposite. And that simple, dependable rule is where the trouble starts. Because if energy always makes matter and its opposite in equal amounts, and the early universe was nothing but energy turning into matter, then the books should balance. Everything made should have an equal and opposite twin. The whole sky should add up to 0. It does not. And the machine that proved the rule is the same machine forcing us to ask why the rule did not hold. To understand why that should frighten anyone, you have to watch the opposite happen. You have to watch matter and its twin come back together. The twin has a name. It is called antimatter. For every kind of particle that builds the ordinary world, there is an anti-version. The electron, the tiny charge that flows through every wire and lights every screen, has a partner called the positron. Same mass, exactly. Opposite charge. In every way a mirror of the thing you are made of. Keep them apart and nothing happens. A positron on its own is a perfectly stable, ordinary speck of the universe. It can sit there. It can move. It behaves. But bring it near an electron, and there is no slow reaction, no fizzing, no decay. The two simply cease to be. In the instant they touch, both particles vanish completely, and in their place there is light. Pure radiation, flying off in opposite directions, carrying away every bit of the mass that used to be there. This is the cleanest event in nature. Matter does not break apart into smaller pieces. It is not transformed into some other stuff. It is converted, all of it, with perfect efficiency, into energy. Nothing is wasted, and nothing is left behind. There is a famous line that tells you how this works, written by a young clerk in a patent office. Energy equals mass times the speed of light squared. People quote it without feeling it, but annihilation is that equation made real and made violent. The speed of light is an enormous number, and you square it, and that is the rate at which a scrap of mass turns into raw energy. A tiny amount of matter holds a staggering amount of power, locked up, waiting. A single gram of matter meeting a single gram of antimatter would release more energy than the bomb that flattened a city. 2 small specks you could hide under a fingernail. The most concentrated release of energy that physics allows, with no leftover ash, no fallout in the ordinary sense, just a flash and then nothing where the matter used to be. This is why antimatter sounds like science fiction. It is the perfect fuel and the perfect weapon, and people have dreamed about both. But the dream runs into a wall. And the wall is the whole point of this story. There is almost no antimatter anywhere to use. The universe will not give it to you. You can search the planet and you will not find a vein of it in the ground. You can sweep telescopes across the galaxy and you will not find a star made of it, or a cloud of it drifting between the stars. If a large lump of antimatter existed out there and drifted into an ordinary gas cloud, the annihilation would blaze across the sky in a way we could not miss. We have looked. The sky is quiet. So here is the world as it actually is. The reaction that destroys matter is simple, total, and everywhere possible. The substance that triggers it is almost completely absent. The universe is built from one side of a pair, and the other side is gone, which leaves a question that will not let go. If energy always makes the two together, and the one destroys the other on contact, then where did all the antimatter go? And why are we still here to ask? The strange thing is that the answer to where antimatter went is not entirely a mystery, because we can make it ourselves. We do it on purpose every working day, in that same complex of tunnels and halls near Geneva. There is a building there with a plain and honest name. People call it the Antimatter Factory. It is not a metaphor. It is a factory in the literal sense. It manufactures the opposite of ordinary matter, and it does so on a schedule. The recipe is brutal and simple. You take protons, the same protons the big collider uses, and you fire them into a block of metal. Most of the energy of that impact scatters as heat and ordinary debris, but a small fraction of it does what energy does in these conditions. It turns into matter and antimatter in pairs, and among the spray of new particles are antiprotons, the mirror of the proton, carrying the opposite charge. Catching them is the hard part. The antiprotons come out moving fast and pointed in every direction, mixed in with ordinary junk. So the factory uses rings of magnets to sort them out, slow them down, and herd the antiprotons into a thin, cold beam. Step by step, the beam is calmed until the antiprotons are crawling instead of racing. Then comes the part that still feels impossible when you say it plainly. The factory takes these antiprotons, adds the anti-version of the electron, and lets them settle together into a complete atom, not a fragment. A whole, stable atom of anti-hydrogen, the simplest element in the universe rebuilt entirely from the wrong side of the mirror. And the moment it exists, it becomes the most dangerous thing in the room, not because it is powerful, but because it is fragile. That anti-atom cannot touch anything. Not the walls of the chamber, not a stray molecule of air, not the equipment that made it. The faintest brush against ordinary matter, and it annihilates. Gone in a pulse of light, taking an equal scrap of the ordinary world with it. So they hold it without touching it. The anti-atom sits inside a trap built from magnetic fields, suspended in a vacuum pumped emptier than deep space, kept colder than almost anywhere in the cosmos. There is nothing under it and nothing around it. It floats, pinned by force alone, while instruments watch from a careful distance. This is the quiet horror of the place. A few atoms of the universe's opposite, held in the dark, in a cage made of nothing, by people who know that one slip ends them in a flash they could not catch. But notice what it took to get there. The full effort of the largest scientific organization on Earth. Custom machines, years of work, and the prize, after all of it, is a handful of atoms that live for a short while before they are lost. We make antimatter one painful piece at a time, and we count ourselves lucky to hold a few of them at once. That tells you something the equations already hinted at. Antimatter is not exotic because it is rare in some accidental way. It is rare because the universe got rid of nearly all of it. We are scraping it back into existence by hand, in tiny amounts, against the grain of everything around us. And that forces the real question into the open. We can build the twin. The early universe built it too, in floods, with the same rule that energy makes pairs. So the universe once had as much of this stuff as we are now struggling to make a few atoms of. More. Far more. And then it lost almost all of it. The question is no longer where antimatter went. It is why the loss was not total. To see how strange that loss is, picture the universe at its very beginning, before there were atoms or stars or any structure at all. There was just energy. An almost unimaginable density of it, packed into a space that was expanding and cooling at a furious rate. An energy, as the collider shows us every day, does not stay as energy when it is that hot. It turns into matter, into particles, born out of the heat, but never one particle, always a pair. This is the rule, and the early universe followed it without exception, because it is not a habit or a tendency. It is built into the structure of physics. When a piece of energy becomes matter, the books must balance. Every quantity the universe keeps track of, every kind of charge, has to come out even. The only way to do that is to make the particle and its opposite together, so that their charges cancel and the ledger reads 0. So the young universe was a storm of creation. pairs of particles flashing into being out of the energy field, a thing and its anti-thing, again and again, everywhere at once. And because it was still ferociously hot, the reverse happened just as fast. Those pairs would meet, annihilate, and turn back into energy, which would then make new pairs, matter and antimatter and light, trading places, over and over in perfect balance. That balance is the whole point. There was no reason for the universe to favor one side. The matter and the antimatter were made in the same instant, from the same energy, by the same rule. They had the same mass. They behaved, as far as anyone could tell from the laws as written, in exactly the same way. If you had stood in that early fire with a perfect set of scales and weighed the matter against the antimatter, the needle should have sat dead center. This is not a guess we are forced to make to fill a gap. It is what the equations predict and what the experiments confirm. Every time we recreate those conditions, in the collider, in the factory, in every test ever run, the pairs come out even. We have never once seen energy make a particle without making its opposite alongside it. The symmetry is one of the deepest and best tested rules in all of science. So the early universe should have been a place of exact equals. For every speck of matter, a speck of antimatter, made together and bound by the same fate. And then the universe cooled. As it expanded, the temperature dropped, and at some point the heat was no longer high enough to make fresh pairs out of the energy field. Creation stopped, but destruction did not. The matter and antimatter already there kept finding each other and annihilating, turning back into light, and now nothing was replacing them. If the two sides were truly equal, the outcome is not in doubt. Every particle of matter had a partner of antimatter waiting somewhere in that dense sea. As the universe thinned out, the partners would find each other. Every electron meets a positron. Every proton meets an antiproton. Each pair touches, vanishes, and becomes light. A perfect, equal birth leads to one place and one place only. Complete cancellation. A universe that builds itself up out of energy and then, as it cools, erases itself back down to radiation, leaving nothing solid behind at all. That is what the rules demand. An empty, glowing universe with no matter in it. By every law we trust, that is the universe we should be living in. So look around at the universe we actually got. There is a floor under you, made of rock and iron, holding up everything you have ever stood on. There is a star 93 million miles away, pouring out the light that grew the food you ate today. There are more stars than there are grains of sand on every beach on Earth, gathered into galaxies, spread across a sky so deep that some of the light reaching us tonight left its source before the Earth existed. And there is you. The matter in your hands, your bones, the part of your brain reading these words. All of it solid. All of it here. None of it cancelled. By the rules we just walked through, none of this should exist. The matter that makes you should have met its antimatter twin in the first second of the universe, and vanished into light long before there were atoms, let alone planets, let alone people. The early cosmos was a near-perfect balance, and a near-perfect balance annihilates itself down to nothing. This is not a small discrepancy at the edge of some experiment. This is everything. Every galaxy, every star, every atom of every living thing, the entire material universe, stands as a violation of the simplest reading of our own physics. We are not a footnote to the laws. We are the exception the laws say should not be there. And no one walking through those tunnels near Geneva can tell you, with certainty, why. That is the part that sits coldest. This is not an obscure puzzle that only specialists worry about. It is the largest unsolved problem about existence itself. The question of why there is something rather than the bright, empty nothing the equations call for. And the people best equipped on the planet to answer it, with the most powerful machine ever built at their command, will tell you honestly that they have a piece of the answer and not the whole of it. Something happened in that first fraction of a second. The balance, which should have been exact, was not. The matter and the antimatter were made together, and they annihilated together, almost all of it, in a wave of destruction that swept the early universe clean. But not quite clean. A trace was spared. A tiny excess of matter, and matter only, survived the fire because there was no antimatter left to cancel it. Everything you have ever seen or touched is that survivor. The leftover. The scrap that was not erased. And the size of that scrap is its own kind of horror, because it tells you how close the universe came to being nothing at all. The survival was not a near thing in our favor. It was a near thing the other way. The universe wanted to be empty, and it almost was. So the question stops being abstract here and turns personal. The matter you are made of is the ash of a fire that consumed nearly everything else. You are sitting on the small remainder that the laws of physics, as we understand them, say should never have been left over. Which means there is a rule we are still missing. A reason the balance broke. And every place we have gone looking for it has only made the gap stranger. Put a number on the survival, because the number is where it stops being a feeling and becomes a measurement. For a long time, the leftover was just an idea, the only way to explain a universe with stuff in it. But it is not only an idea anymore. We can read the size of the original imbalance straight off the sky. When the early universe finally cooled enough for the annihilation to finish, all that destroyed matter and antimatter turned into light. That light is still here. It has been traveling ever since, stretched out and dimmed by the expansion of space, and it now fills the whole sky as a faint hiss of radiation, the oldest light there is. We can measure it precisely. It is the leftover glow of the Great Cancellation. So we have two things we can count. We can count the matter in the universe, in all the stars and gas and galaxies. And we can count the light, the radiation left behind, when matter and antimatter destroyed each other. The ratio between them tells us the original recipe. For every particle of matter that survived, you can work out how many particles of light the annihilation produced, and that number is the fossil record of how lopsided the early universe really was. Here is what it says. In the first moments, for roughly every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. Sit with the smallness of that. Not 2 to 1, not a clear majority. One extra out of a billion. For every billion pairs of matter and antimatter that found each other and annihilated into light, a single particle of matter was left standing with no partner to destroy it. The rest cancelled out completely. That 1 in a billion is everything. That is the entire material universe. Every galaxy in the deep sky, every star, every planet, the Earth, the oceans, all of life, you are built out of the survivors of that lopsided count. The 1 extra in each billion is the whole of what remains. The other billion went into the light that now fills the dark between the stars. So when you look up at the night sky and feel how full it is, how crowded with stars, you're looking at the thin remainder. The universe annihilated about 1 billion times more matter than it kept. What we call everything is the rounding error, and that reframes the entire problem with a sharper edge. The mystery was never why so much was destroyed. Destruction is easy to explain. Equal amounts of matter and antimatter will always annihilate. The mystery is the leftover one. Where did that single extra particle in each billion come from? Why was the count not exactly even 1 billion against 1 billion, leaving nothing? Because if it had been even, and every reason in physics says it should have been, then there is no survivor, no remainder, no rounding error to build a cosmos from. The sky is only light, and there is no one beneath it to notice. A difference of 1 part in a billion is the line between a universe and an absence, and nothing in the simple rules accounts for it. The equations make pairs. They do not make an extra. They have no slot for the one survivor in each billion that turns out to be the source of you. So somewhere in that first fraction of a second, the universe broke its own symmetry. Slightly. Just enough. And finding the crack became the work of the most sensitive machines ever built. The word for what went wrong is symmetry, and it helps to be exact about what that means here. Because it is the hinge. The whole story turns on. A symmetry in physics is a rule that says you can change something and the laws will not notice. Flip the universe in a mirror, left for right, and gravity still works. Light still moves. The equations hold. Swap a particle for its antiparticle, matter for antimatter, and the same thing should be true. The laws are supposed to treat the two sides identically. Neither one is favoured. That fairness is the symmetry. For most of the history of physics, this was taken as close to sacred. The universe was thought to be perfectly even-handed. It should not care whether you are made of matter or antimatter, any more than it cares whether you write with your left hand or your right. Run any process forward with matter, run it again with antimatter, and you should get mirror image results, identical in every way that counts. But a universe that is perfectly even-handed cannot end up lopsided. That is the trap. If matter and antimatter obey exactly the same laws, then whatever made the matter made the antimatter in the same breath and the same amount, and the two cancel without remainder. To get leftover, the symmetry has to fail. The laws have to care just a little about the difference between a particle and its twin. They have to treat matter and antimatter slightly differently, so that when the dust settles, there is a touch more of one than the other. This is the crack the survival demands. For us to be here, the mirror has to be flawed. Somewhere in the rules of nature, there must be a process that runs a hair faster, or a hair more often, for matter than for antimatter. Not by much. A part in a billion is enough, but it cannot be zero, or we are not here. For years, this was a logical necessity and nothing more. Physicists knew the symmetry had to break because they were standing in the proof of it, made of the leftover. What they did not have was any evidence that the laws actually behaved this way. Every experiment they could run showed matter and antimatter acting as perfect mirrors. The symmetry held in the lab, flawlessly, while the entire universe stood as evidence that it must have failed at least once. That is a deeply uncomfortable place to be. You have a conclusion you cannot escape, a symmetry that has to break, and a stack of results that all say it does not. Either the laws of physics had a flaw no one had ever seen, or the entire material universe was a contradiction. So the search began, not for the source of the imbalance directly, but for any sign at all that the mirror was cracked. Any process, anywhere, no matter how small, where matter and antimatter did not behave as exact opposites. A single crack would prove the rule could fail. It would turn the survival from a paradox into a clue. And the strange truth is that the crack was found. The mirror does break. Nature does, in certain rare moments, treat matter and antimatter differently. It was caught, First, in a particle most people have never heard of, and the discovery rattled physics enough to win the people behind it the highest prize in the field. But finding the crack only deepened the dread, for a reason that will take the rest of this story to lay bare. The mirror breaks. We have watched it break, and the breaking we can see is nowhere near enough. The first crack showed up in a particle called the kaon, and the story of how it was found has the shape of an accident. A kaon is a short-lived particle, not part of ordinary matter, made when other particles collide with enough energy. It belongs to a family that physicists once labeled strange, because the particles behaved in ways the early theories did not expect. Kaons are unstable. They exist for a flicker of time and then decay, breaking apart into lighter particles. And there is an anti-version, the anti-kaon, the mirror image, which should decay in a perfectly mirrored way. A team in the United States set out to study these decays in detail. They were not hunting for a broken symmetry. Most physicists at the time were confident the mirror was perfect. That matter and antimatter were exact opposites in every process. The experiment was meant to confirm that confidence, to measure the decays carefully and tick the box. It did not tick the box. When they watched the kaons decay, a tiny fraction of them went down a path that the perfect mirror forbade. The matter and antimatter versions were not behaving identically. There was a small, stubborn difference, a handful of decays out of thousands that broke the symmetry the whole field had assumed was unbreakable. The effect was minute. It showed up in roughly one decay out of 500. But it was real, and it would not go away. And its meaning was enormous. For the first time, an experiment had caught nature treating matter and antimatter differently. The mirror was not perfect. It had a flaw, built into the laws themselves. The two physicists who led the work were honored with the highest prize in science for it. And rightly so, because they had found something the universe needed in order to exist. Here, at last, was proof that the symmetry could break. The leftover matter that built the cosmos no longer had to be a contradiction. There was a real, measured process where matter and antimatter parted ways, however slightly. It should have felt like the door swinging open. In a sense, it did. The discovery told physicists exactly what to look for and where the answer might live. The crack in the mirror was woven into the behavior of certain heavy, unstable particles. And if they studied those particles closely enough, they could measure the imbalance and trace it back to the early universe. But there was a quiet problem hiding in the celebration, and it grew louder the more the numbers were examined. The crack was there. It was just small, very small. A difference of 1 part in 500 in the decays of a rare particle is a long way from a difference that could survive the annihilation of nearly an entire universe and leave behind every star. Still, you do not solve a problem like this in a day. The crack was proof of principle, and physics had a target now. The next step was obvious. Build something tuned to watch the mirror break, not by accident but on purpose, again and again, with enough precision to measure exactly how unequal matter and antimatter really are. And so the search moved to a place where the heaviest of these particles could be made in floods, and a detector was built for the single purpose of weighing matter against its twin. At one of the 4 points where the Great Collider crosses its beams, a detector waits that does not look like the others. The famous ones are built like onions, layer wrapped around layer, surrounding the collision point on every side to catch everything that flies out. This one is built off to a side, long and forward-leaning, shaped to look in a single direction. There is a reason for the odd shape, and it comes straight from the kind of particle it hunts. This detector was built to study the heaviest version of the strange family, particles that carry what physicists call beauty, a heavy cousin of the quarks inside ordinary matter. When the collider smashes protons together, these heavy particles are born in the wreckage, and they tend to fly forward, close to the original line of the beam, rather than spraying out sideways. So the detector reaches forward to catch them, like a hand cupped in a stream. These beauty particles are the richest place in nature to watch the mirror break. They are heavy, which means they can decay in many different ways, down many different paths, and in the rules of physics, the crack between matter and antimatter shows up most strongly in exactly these kinds of decays. The kaon gave the first hint with its tiny 1 in 500 difference. The beauty particles promise to show the same flaw, larger and clearer, across a whole menu of decays. But to read that flaw, you cannot study one particle. You need a tide of them. A beauty particle lives for about a trillionth of a second before it falls apart. Far too short a time to see directly. What the detector sees is the spray of lighter particles left when it decays, and from those tracks it reconstructs what was there a moment before. To measure a difference of a fraction of a percent between matter and antimatter, you have to do this not once but billions of times, building the count up until the small imbalance rises out of the noise. That is what the machine is for. The collider produces these heavy particles by the billions. The detector catches the ones that fly forward, tracks every fragment of their decays with a precision measured in fractions of a hair, and tags whether each one was matter or antimatter. Then it does it again and again around the clock, for years, stacking the numbers higher and higher. It is patient work, and it is unforgiving. A single mistake in telling matter from antimatter, repeated across billions of events, would fake an imbalance that was never there, or hide a real one. So the detector is built to be almost paranoid about the difference, checking and rechecking which side of the mirror each particle came from. The purpose behind all of it is simple to state, even if the machinery is not. Take the heaviest, rarest particles the collider can make. Watch them decay. Compare with brutal care how the matter versions behave against how the antimatter versions behave, and measure the gap. Because the gap is the whole story. If matter and antimatter were perfect mirrors, the gap would be zero, and we would not exist. The crack found in the kaon says the gap is not zero. The detector built for beauty was made to measure it precisely, to find every place the mirror cracks, and to add it all up. The hope, unspoken but real, was that the total would be large enough to explain us. That if you found enough cracks, and measured them well enough, the imbalance would come out matching the 1 in a billion written across the sky. The first thing to understand is how that measurement is actually made. Because it is simpler than it sounds. And the simplicity is what makes the result so hard to escape. Strip away the machinery and the measurement comes down to a single, almost childlike comparison. You make a heavy particle and you watch how it falls apart. You make its antimatter twin and you watch how it falls apart. Then you ask whether the two did the same thing. Take a beauty particle. It is unstable, so it decays, and it can break apart in several different ways, into different sets of lighter particles. Think of it like a die that can land on several faces, except the faces are decay paths. The particle does not choose freely. The laws of physics set the odds. A certain fraction of the time it goes one way, a certain fraction another. Now make the anti-version, the mirror image, and let it decay. If matter and antimatter are perfect opposites, the antiparticle must land on the mirrored faces with exactly the same odds. The same fraction down each path. Whatever the matter did, the antimatter does in perfect reflection. That is what a clean symmetry would mean. Identical odds every time. So the experiment counts. It collects huge numbers of the matter particles and sorts their decays by path, working out what fraction went each way. Then it does the same for the antimatter particles, and it lays the two sets of fractions side by side and looks for any path where they do not match. Most of the time they match closely, and that itself is a measurement worth having. But on certain paths, in certain decays, they do not. The matter version favors one route a little more often than the antimatter version favors the mirrored route. Out of millions of decays, one side runs slightly ahead. The fractions are close, but they are not the same, and the difference holds up no matter how many times you repeat the count. That gap, that slight preference of matter for one path over the mirrored path the antimatter takes, is the broken symmetry made visible. It is the crack in the mirror, measured as a number, not inferred, not argued for, counted directly by tallying how a particle and its twin chose to fall apart. The reason this measurement is so trusted is that it does not rely on theory to interpret it. You are not modeling anything exotic. You are counting decays and comparing two columns of numbers. If the columns differ, the symmetry is broken. Full stop. The collider makes the particles in such floods that the counts run into the billions, and a difference of even a fraction of a percent rises cleanly out of that ocean of events, far above any chance fluctuation. And the experiment has done this many times now, across many different beauty particles and many different decay paths. The mirror does break. The matter and antimatter twins do not always fall apart the same way. The effect first glimpsed in the kaon shows up here too, larger and clearer, exactly where the theory said it would. Each new measurement confirms it. Matter and antimatter are not perfect opposites. There is a real, repeatable, built-in preference. For a while, this looked like a march toward the answer. Every result fit. The crack was real, the theory predicted it, and the measurements kept lining up with the prediction to remarkable precision. The mirror breaks, we can measure exactly how much, and the numbers agree with the equations beautifully, which is precisely where the flaw falls out. Because the same equations that predict these cracks so well also predict their total size. And when you add up every crack the detector has ever found, every difference between matter and antimatter the theory allows, the sum is not close to enough. Here is the number that should not be skipped over, because it is the heart of the dread. The cracks are real. The theory that describes them, the framework that has passed every test physicists have thrown at it for decades, predicts them and gets them right. When the detector measures how much matter and antimatter differ in their decays, the result agrees with the equations to a precision that should be a triumph. The mirror breaks by exactly the amount the leading theory says it should. And the amount the leading theory says it should is far too small to have made you. This is the result that quietly undoes the celebration. The broken symmetry we can measure, the crack in the mirror that we have caught and counted and confirmed, produces an imbalance between matter and antimatter that falls vastly short of the 1 in a billion written across the sky. Not a little short. Not within reach of some refinement or a better measurement. Short by a margin so large, it stops being a discrepancy and becomes a wall. Run the calculation forward. Take the broken symmetry exactly as we measure it, with all the cracks the theory allows, and ask how much leftover matter it would have produced in the early universe. Ask how lopsided the great annihilation would have been. The honest answer is that it would have produced almost nothing. A leftover so tiny that the universe would have annihilated itself down to a faint haze of light and a scattering of stray particles too thin to ever form a single star. The symmetry breaking we have found is genuine, and it is genuinely insufficient. It is the right kind of effect, in the right direction, doing exactly what it must. And it is nowhere near strong enough to do the job. We caught the mechanism that lets matter outlast antimatter, and then we discovered the mechanism is too weak by an enormous factor to account for the matter that exists. So the most powerful machine ever built, after billions of collisions and years of measurement, has confirmed two things at once. The mirror does break, and the breaking we can see could never have made the universe. That is a strange and lonely place for a science to stand. Physics found the clue it needed. The proof that matter and antimatter are not perfect opposites. And the clue turned out to be a near miss. It points at the answer without being the answer. It tells you the kind of thing that must have happened in the first second, while making it brutally clear that the thing we can measure is not big enough to have happened the way it needed to. If you have been wondering how a question this large stays unanswered, this is how. We are not lacking the first clue. We found that long ago. We are lacking a second, much larger source of imbalance, one that the universe clearly used, and that none of our experiments has ever managed to see. The known cause is too small to save us. And the gap between what it explains and what needs explaining is not a small gap. It is one of the widest gaps in all of science, and putting a real scale on it is the only way to feel how empty the explanation truly is. So scale it. Numbers like too small can hide their meaning until you force them into the open, and this one is worth forcing. The imbalance the universe actually had, the leftover written into the oldest light, is the one in a billion. One extra particle of matter for every billion pairs that annihilated. That is the target. That is the amount of broken symmetry the early universe must have produced for there to be stars and planets and people. The imbalance the known crack in the mirror can produce, calculated straight from the theory that fits every measurement, is smaller than the target by a factor in the range of 10 billion. Some estimates land near a billion, some far past it depending on the details, but the order of the thing is not in dispute. The symmetry breaking we have measured falls short by something close to 10 orders of magnitude. That phrase, 10 orders of magnitude, slides past easily, so slow it down. Each order of magnitude is a factor of 10. 10 orders of magnitude is a 1 followed by 10 zeros. It is the difference between a single second and 3 centuries. It is the difference between a sip of water and a small lake. The mechanism we found, set against the job it has to do, is off not by a comfortable margin, but by a factor of around 10 billion. Picture it another way. Imagine you needed to fill a swimming pool, and the only tool anyone could find, after the most thorough search in the history of the field, was an eyedropper. You can prove the eyedropper works. You can watch it release a drop. The drop is real, and it is so far from filling the pool that the comparison is almost a joke. Except that the pool is the universe and the water is the reason anything exists. This is the true shape of the problem, and it is worse than a simple gap in knowledge. It is not that we have no explanation. It is that we have an explanation, a real and confirmed one, and it accounts for roughly 1/10 billionth of what needs explaining. The rest, the overwhelming bulk of the imbalance that built the material universe, comes from a source we have never identified, never measured, and never seen behave. If you ever want a single fact to carry the weight of this whole story, it is this. The cause of matter we understand is about 10 billion times too weak to have made the matter we are. Everything you can touch sits on top of a missing explanation that dwarfs the one we have. That is the dread, stated plainly. Not mystery in the cozy sense, a puzzle waiting for a clever solution. A measured, quantified shortfall where the best science on Earth can show you the size of its own ignorance to 10 decimal places and tell you, with confidence, that the answer's out there and that we have found almost none of it. If this is the kind of question that keeps you up at night, the channel is built for it, and following along means you will be there as the search continues. The shortfall does one useful thing though. It tells us, beyond any reasonable doubt, that there is a second cause. The universe used something we have not found, which means somewhere in some process we have not yet caught, the mirror must crack again, harder, in a way the known theory does not contain. Frame it as the search now becomes, because the shortfall changes the question entirely. For a long time, the goal was to prove the mirror could crack at all. That is done. The kaon proved it. The beauty particles confirmed it. The theory predicts it. The crack is settled science. But the crack we know is a near miss by a factor of 10 billion. So the goal is no longer to find a crack. It is to find a different one. A second source of imbalance, hidden somewhere we have not looked carefully enough, large enough to make up the staggering difference between the matter that exists and the matter the known physics can account for. Physicists call this missing piece by a careful name. They say the universe needs a new source of symmetry breaking, beyond the one written into the current theory. Beyond, because the theory we have, for all its precision, is now known to be incomplete. It describes the particles and forces we have found with breathtaking accuracy, and it cannot make a universe with anything in it. The most successful theory in the history of physics fails at the single task of explaining why there is something rather than nothing. That word, incomplete, is doing heavy work, and it is worth being honest about how it feels from the inside. This theory has predicted the existence of particles before they were found. It has matched measurement after measurement to more decimal places than almost any idea in science. It is, by every internal measure, a stunning success. And it is missing something so large that the entire material universe stands outside its reach. So the hunt turns outward. If the imbalance we can measure is too small by 10 billion, then there must be physics we have not discovered. New particles, perhaps, that existed in the early universe and tipped the balance before they decayed away. New forces that acted only in that first fraction of a second. New cracks in the mirror in places the current theory says should be perfectly smooth. This is where the search gets genuinely frightening, and not because of anything dramatic. It gets frightening because of where the hunters have to look. The known cracks live in the decays of particles the collider can make. To find a larger crack, you go to rarer decays, fainter signals, processes that happen so seldom that you might watch a trillion events to catch a handful. You push the precision of the measurement past anything attempted before, hunting for a difference between matter and antimatter so subtle that the current theory predicts it should not be there at all. Because that is the prize. Not another confirmation of the crack we know, but a deviation. A place where matter and antimatter behave differently than the theory says they should, even by a hair. That hair would be the thread leading to the missing cause. It would be the first direct sign of the new physics the universe is forcing us to believe in. The logic is airtight, and that is what unsettles. We are not guessing that something is missing. The shortfall guarantees it. There is a second source of broken symmetry. It has to exist, because we are here, and the known cause cannot account for us. The only question is where it hides and why every attempt to catch it has come up matching the old theory exactly. And there is one more recent twist, a place where the mirror was found to crack in a way it had never been seen to crack before. It made headlines. It was real. And it changed less than the headlines suggested. The newest crack showed up where no one had ever caught it before, in a kind of particle that, until recently, had kept its mirror perfectly intact. Everything found so far, the kaons and the beauty particles, belong to one broad family. They are made of two quarks bound together, a quark and an antiquark, a particle and a piece of antimatter joined in a short-lived pair. The crack in the mirror had only ever been seen in these two quark particles, never in the other great family of matter, the one that actually builds the world. That other family is the baryons. A baryon is made of three quarks, not two, and it is the kind of particle that matters most to us, because the protons and neutrons inside every atom are baryons. The ordinary matter you are made of is baryonic matter. So the question of why matter outlasted antimatter is, at its root, a question about baryons. Why are there more baryons than anti-baryons? Why is the world built of three quark particles and not their mirror twins? And in all the decades of searching, the mirror had never once been seen to crack in a baryon. The effect showed up reliably in the two quark particles, but the three quark particles, the ones that actually make up the universe, had always behaved as perfect mirrors. Matter baryons and antimatter baryons fell apart the same way, every time, within the precision anyone could reach. That changed. The detector built for beauty, after gathering enough heavy baryons and their anti-twins to make the comparison, finally caught it. A heavy baryon and its antimatter version decayed at measurably different rates down certain paths. For the first time, the broken symmetry was seen in the kind of matter that actually builds atoms. The mirror cracks in baryons too. This was a genuine milestone, and the field treated it as one. The crack had finally been found in the right family. The family that the whole mystery is really about. After years of seeing the effect only in the lighter, two quark particles, here was direct proof that the three quark matter of the everyday world also breaks the symmetry. It closed a gap that had stood open for a long time. And then you check the size of it, and the floor that you thought was finally solid gives way again. The crack in the baryons, real and historic as it is, comes out matching the predictions of the same old theory. It is the right kind of effect, in the right family at last, and it is still bounded by the framework that we already know is 10 billion times too weak. Finding the crack in baryons confirmed that the theory works where it had not yet been tested. It did not produce the missing source. It did not close the gap. So the search stands exactly where the shortfall left it, only with one more confirmation that the known physics is right and still not enough. The mirror cracks in beauty particles. The mirror cracks in baryons. Everywhere we look, it cracks by precisely the amount the theory predicts, and precisely the amount that could never have built the universe. We keep finding the crack in new places. We keep finding it the right size to be useless. And the place where the larger crack must hide grows quieter the harder we listen. If the missing crack will not show up in the ordinary decays, then you go after the decays that almost never happen. That is the next move, and it tells you how far the search has been pushed. Some decays are common. A particle falls apart the way it usually does, down a well-worn path, billions of times. Others are rare. The laws allow them, but only barely. So they happen once in millions, or once in billions of chances. And it is exactly these rare decays where new physics is most likely to leave a mark. because there is so little ordinary activity to bury it. A faint new effect that would be invisible in a common decay can stand out in a rare one, the way a whisper carries in a silent room. So the detector spends years hunting decays that the theory says should happen only a handful of times in a billion. To see them at all, the collider has to produce the parent particles in numbers that are hard to hold in the mind. You make trillions of the heavy particles, you watch them all fall apart, and you wait for the few that take the forbidden-looking path. Then, you count those few with the kind of care normally reserved for things that matter more than a number ever should. There is a particular decay that physicists watched for decades. One so rare it was a kind of holy grail. A heavy particle that should, according to the theory, decay into a specific pair of lighter particles only about 3 times in every billion. If new physics were hiding nearby, some unknown particle or force whispering into the process, that rate would come out wrong, higher or lower than the theory predicts. A wrong number here would be a direct fingerprint of something beyond the known world. They caught the decay. After years of collecting, the rare event finally rose out of the noise, seen clearly for the first time. It was a real achievement, the kind that takes a generation of work. And the rate came out right. Almost exactly the 3 in a billion the theory predicted. No fingerprint, no whisper. The new physics that should have shifted the number left no trace. This is the pattern that begins to wear on people. The precision is staggering. The experiments reach into processes that happen a few times in a billion and measure them well enough to test the theory to several decimal places. And every time, the theory holds. The rare decays behave. The forbidden-looking paths turn out to be just as forbidden as predicted. Nature keeps passing a test that was designed to catch it cheating. Each of these measurements is, on its own, a triumph of human patience and skill. To pull a 3 in a billion signal out of trillions of collisions and pin its rate to within a few percent is one of the most delicate things our species has ever done. And the result of all that delicacy is a long, growing list of confirmations that the theory we already know is right, in places we had never been able to check before. But right is not the prize. The prize is wrong. The whole search depends on finding a place where the theory fails, where matter and antimatter, or the rates of rare decays, come out different from prediction. That failure would be the thread to the missing cause. And the rare decays, the most sensitive probes ever built, keep coming back clean. So the precision climbs, and the deviations do not appear. And a quieter and stranger problem starts to take shape behind the search itself. The unease has a name among physicists, even if they rarely say it out loud in those words. The theory keeps matching, everything keeps matching, and the matching is the problem. Step back and look at the whole record. The decays of the beauty particles match the theory. The newly found crack in the baryons matches the theory. The rare decays, watched for decades, match the theory. Measurement after measurement, across the most powerful machine ever built, comes back agreeing with the framework we already had. The needle lands on the predicted value again and again with a precision that should be the pride of the field. And it would be, except for one thing. We know the theory is wrong. Not wrong in its details, which are tested to absurd precision, but wrong in its completeness. It cannot explain why there is matter at all. It is off by a factor of 10 billion on the single question of why the universe is not empty. So every time it passes another test, the field is caught in a contradiction it cannot resolve. The theory is confirmed, and the theory is broken, in the same breath, by the same experiments. This is not how discovery is supposed to feel. The usual story of physics is that you build a better instrument, you look closer, and the universe surprises you. A new effect appears, the old theory cracks, and through the crack, you glimpse something larger. That is how the kaon happened. That is how nearly every leap forward happened. You expect the next machine to break the old picture and show you the new one. The most powerful machine ever built was supposed to do exactly that. It was meant to find the new physics, the heavier particles, the deviations that would point the way to why matter survived. And instead, it has spent its life confirming the old picture with ever finer precision. While the question that justified building it stays exactly as unanswered as before, there is a particular dread in being right too often. A theory that fails in an interesting place gives you somewhere to go. A theory that succeeds everywhere you can reach, while failing at the one thing that matters most, leaves you standing in a hall of confirmations with no door out. The matching is not comfort. It is a wall, built higher with every measurement, between us and the answer we know must be on the other side. And it raises a possibility that no one likes to dwell on. Maybe the missing physics does not live anywhere the collider can reach. Maybe the new particles, the larger crack in the mirror, the source of the matter that built us, sit at energies so far beyond this machine that no collision it can produce will ever touch them. Maybe the reason everything matches is that the part of nature we need is simply too far away to disturb. That would be a strange kind of defeat. Not a wrong answer, but a confirmed silence. A universe that tells you, through its own flawless behavior, that the thing you are looking for is real and out of reach. The matching is the first layer of the silence. There is a second, and it is louder, because it concerns a whole crowd of particles that the smartest people in the field were nearly certain they would find by now. For decades, there was a confident prediction about what the collider would find, and it was not just the crack in the mirror. It was a whole new layer of the universe, a set of undiscovered particles that most physicists expected to appear the moment the machine reached high enough for energy. They have not appeared. The space where they should be is empty, and the emptiness has a weight of its own. The prediction came from trying to fix the very problem we have been circling. The known theory is incomplete. It cannot explain the matter imbalance, and it has other deep troubles besides. So theorists spent years building extensions to it, deeper theories that would solve those troubles, and nearly all of the most promising ones made the same promise. They predicted new particles, heavier partners to the ones we know, a hidden doubling of the particle world, sitting just above the reach of the older machines and squarely within the reach of the new one. These new particles were not a wild guess. They were the natural consequence of the most elegant ideas for completing physics. Ideas so attractive that a generation of theorists became confident they described reality. The particles had a role to play. They would have steadied the theory, fixed its internal flaws, and in many versions, they would have supplied new cracks in the mirror, new sources of the matter imbalance, perhaps even the missing one. They were supposed to be the answer, and the collider was supposed to be where we met them. The machine reached its energy. It ran for years. It produced collisions at scales never achieved before, exactly where the new particles were expected to show themselves. And it found the particles we already knew, and nothing else. No heavier partners, no hidden layer. The new world that was supposed to be waiting at high energy did not show up. This is the Great Silence, and it is hard to overstate how much it has unsettled the field. An entire framework of expectation, built over decades, predicting a rich new layer of reality, met by an empty result. The collisions that were supposed to open the door opened onto more of the same. Physicists who had spent careers preparing to study the new particles found there were no new particles to study. It is worth being clear about what was and was not found. The machine made one enormous discovery, a particle that completed the known theory, and we will come to it, because it carries a horror of its own. But beyond that single find, the rich crowd of expected particles, the ones that would have explained the matter, imbalance and much else, simply were not there. So the field is left holding two silences at once. The measurements all match the old theory, and the new particles that were supposed to replace it never arrived. Both of the obvious roads to the missing physics have come back empty. The deviations did not appear, and neither did the new particles that would have caused them. And into that double silence comes the strangest result of all, the one find the machine did make. Sitting at a value so unnatural that to many physicists, it looks less like an answer and more like a sign that something is deeply wrong with the way we understand the world. The one great discovery the collider made is a particle that had been predicted for half a century, the last missing piece of the known theory. Finding it was the machine's triumph, the thing it was most built to do. And the way it turned out has left a quiet horror running underneath the celebration because of where its mass landed. This particle is tied to a field that fills all of space and gives the other particles their mass. Without it, nothing would have weight. And the universe would be a rush of massless things moving at the speed of light, never settling into atoms. So it matters enormously, and confirming it was a real victory. The problem is not that it exists. The problem is how heavy it is, and what its weight implies about the theory around it. In the equations, the mass of this particle should be enormous. Not the modest value that was measured, but something staggeringly larger, driven up by contributions from every other particle and field it touches. The math, taken at face value, says it should be pulled toward the highest energies in nature. A value so large it would have made the universe we know impossible. Instead, it sits at a tiny fraction of that, in a place gentle enough to allow atoms and stars and life. For the measured value to come out where it does, the enormous contributions that should drive it sky high have to cancel against each other almost perfectly. Not roughly. Almost exactly, agreeing to many decimal places, as if a long list of huge numbers added up to nearly zero by sheer coincidence. Physicists call a coincidence like that unnatural, and the word carries real discomfort. A theory that needs a near-perfect cancellation, with no reason behind it, feels to most physicists like a theory that is missing something. This is the unnatural lightness, and it bothered people enough that it was one of the main reasons they expected the new particles in the first place. Those predicted partners would have done a job. They would have balanced the equation naturally, cancelling the runaway contributions for a real reason instead of a coincidence, and settling the particle's mass at the gentle value we see. The lightness would have made sense. The theory would have felt whole, but the new particles did not appear. The lightness is real, measured, and sitting there without the explanation that was supposed to accompany it. The cancellation that should not happen by chance appears to happen by chance, and the natural fix for it has failed to show up at any energy the machine can reach. So, the field is left with a particle it spent 50 years hunting, found exactly as predicted, whose value quietly insists that the theory is incomplete. The triumph and the trouble are the same object. We found the last piece, and the last piece does not fit the way a finished puzzle should. There is a pattern forming across all of this, and it is the real source of the dread. Every place we look, the known physics works beautifully and then points beyond itself. The cracks are the right size and too small. The decays match and the matching is wrong. The last particle is found, and its mass makes no sense alone. The theory keeps succeeding in a way that keeps insisting it is not the whole story. So physicists turn to a different kind of test entirely, not smashing particles, but trapping them and holding the antimatter still long enough to look at it directly. Set the collisions aside, because there is another way to interrogate antimatter, and it is gentler and in some ways more direct. Instead of making heavy particles and watching them shatter, you make the simplest possible piece of antimatter and you hold it still. You trap an anti-atom and you study it at your leisure. This is the work of the Antimatter Factory, the part of the complex built not to collide, but to capture. The goal there is anti-hydrogen, the antimatter twin of the simplest atom in the universe. Ordinary hydrogen is one proton with one electron circling it. Anti-hydrogen is one antiproton with one positron, the same atom built entirely from the wrong side of the mirror. If matter and antimatter differ anywhere, this clean and simple atom is one of the best places to catch the difference. Making it is hard, and holding it is harder. The antiprotons come from slamming protons into metal, then they are slowed and cooled through ring after ring, until they are barely moving. The positrons are gathered separately. Then the two are brought together in a trap and coaxed into joining. An antiproton catching a positron into orbit, forming a complete anti-atom. Only a fraction of the attempts succeed, and the ones that do are precious. The danger is constant. The instant an anti-atom touches anything made of ordinary matter, it annihilates. The walls of the chamber would destroy it. A stray molecule of gas would destroy it. So the anti-atoms are held in a magnetic trap, suspended in a vacuum emptier than the space between planets, cooled until they are nearly motionless, floating in a cage that touches them with nothing but force. Early on, the anti-atoms could be held for only a flicker. With time and care, physicists learned to hold them for many minutes at a stretch. An eternity by the standards of antimatter, long enough to study them properly. And once you can hold an anti-atom still, a whole new kind of question opens up. You are no longer counting how a particle falls apart. You are looking at the atom itself, its structure, its behavior, the way it responds to light and to gravity. You can ask whether an atom of antimatter is, in every measurable way, the perfect mirror of an atom of matter, or whether somewhere in its makeup, a difference hides that the violent collisions could never reveal. That is the promise of trapping. The collider tests the symmetry in the chaos of decay. The trap tests it in stillness and quiet, on a complete atom, where the most delicate differences might surface. If the books do not balance, if matter and antimatter are not perfect opposites, perhaps the imbalance lives not in how they break apart, but in what they fundamentally are. Their weight, their light, their response to the most basic forces in nature. For a long time, these were questions physicists could only dream of testing, because no one could hold antimatter still long enough to ask. Now, they can. And one of the first questions they reached for was the oldest and most basic one of all. A question about something everyone assumes they understand, and almost no one had ever tested on antimatter. Which way does it fall? Drop a ball and you know what happens. It falls. Everything falls the same way, pulled down by gravity at the same rate, a feather and a hammer alike once you remove the air. This is the most familiar fact in the world. And until recently, no one had ever confirmed it was true for antimatter. The question sounds almost too simple to be serious. Does antimatter fall down? But it was a real and open one, and behind it sat a possibility strange enough to be worth checking. What if antimatter fell up? What if gravity, which pulls all ordinary matter together, pushed antimatter away instead? It would have been a wild break from everything expected, and it would have changed the story of the early universe completely. If antimatter were repelled by gravity, it might have fled from matter in the first moments, gathered itself in distant regions of the cosmos, and the great annihilation might never have finished. The missing antimatter might simply be hiding, pushed somewhere far away. It was a long shot, and most physicists doubted it. But doubt is not measurement, and the only way to know which way antimatter falls is to drop some and watch. The trouble again is that you cannot just hold a handful of antimatter over a table and let go. It would annihilate the instant it touched anything. You need anti-atoms, trapped and cooled, and then you need to release them gently and track which way they drift in the time before they hit a wall. That is what the trapping work finally made possible. Anti-hydrogen atoms were held in a tall magnetic trap, cooled to nearly motionless, and then the trap was slowly relaxed, letting the anti-atoms escape. The instruments watched where they went, up or down, and the answer, measured directly for the first time, was down. Antimatter falls. It feels gravity the same way ordinary matter does, pulled downward at the same rate, within the precision of the measurement. This closed a door that some had hoped might lead somewhere. Antimatter does not fall up. It does not hide in distant regions because gravity repels it. There is no secret reservoir of it pushed to the far edges of the cosmos by an anti-gravity no one had measured. The missing antimatter is not somewhere out there, kept apart by a force we had overlooked. It is simply gone, annihilated in the early universe, like the equations always said. In one sense, the result was reassuring, a confirmation that gravity behaves sensibly and the universe is consistent. In another sense, it was one more closed door in a hallway that is running short of doors. Every test like this narrows the places the answer can hide. Antimatter falls like matter. Whatever tipped the balance in the early universe, it was not gravity playing favorites. So the imbalance does not live in how antimatter responds to gravity. The trap had ruled out one hiding place with a clean and direct measurement. But there was another property to check, even more precise, and physicists pushed the trapped anti-atoms toward it. Not how antimatter falls, but the light it gives off. Because if matter and antimatter differ at all in their deepest structure, the light should show it. Light is the most precise messenger in all of physics, and that makes it the sharpest possible test of whether antimatter is truly a perfect mirror. So once anti-hydrogen could be trapped and held, the next move was to shine light on it and read what came back. Every atom has a kind of fingerprint written in light. When you give an atom energy, its electron jumps to a higher orbit, and when it falls back, it releases that energy as light of a very exact color. Not a smear of colors, but sharp, specific lines set by the structure of the atom. Hydrogen has its own pattern of these lines, measured over more than a century to extraordinary precision. One of the most exactly known things in all of science. Every hydrogen atom in the universe sings the same notes. The question was whether anti-hydrogen sings them too. If matter and antimatter are perfect mirrors, the anti-atom must give off light at exactly the same colors as ordinary hydrogen, the same sharp lines in the same places. Any difference, even the faintest shift in a single line, would be a crack in the mirror at the deepest level, a sign that antimatter is not quite the perfect opposite the theory demands. And a difference there might point toward the missing imbalance, the reason matter won. This was a brutally hard measurement. You need the anti-atoms trapped, cooled, and held still, and then You need to hit them with light of an exact color and watch whether they respond, whether they absorb it and jump the way ordinary hydrogen would. With only a small number of anti-atoms to work with, each one precious and fragile, the measurement took the patience of years. But it was done. Physicists measured the light of anti-hydrogen and laid it beside the light of hydrogen, line against line. They matched. To the precision the instruments could reach, the light of antimatter is identical to the light of matter. The same colors, the same sharp lines in the same places. Anti-hydrogen sings the exact notes of ordinary hydrogen. The mirror, at the level of the atom and its light, is flawless, and so another hiding place closes. The imbalance does not live in the light of antimatter. It does not live in the structure of the anti-atom, which is, as far as the most precise tool in physics can tell, a perfect reflection of ordinary matter. Matter and antimatter weigh the same, fall the same, and shine the same. Everywhere the trap looks, the twin is too perfect, matching ordinary matter line for line, with no flaw to explain why one of them survived, and the other did not. This is the quiet shape of the whole search now. In the violent world of collisions, the mirror cracks, but only by the tiny amount the theory predicts. Far too little. In the still world of trapped atoms, the mirror does not crack at all. Gravity, mass, light, structure, every fundamental property tested comes back identical. The difference that built the universe is not in any of these places. So where is it? The imbalance is real, it has to be, because we exist. But it is not in the gravity, not in the light, not in the mass, and the one place it does show up, the decays, is 10 billion times too weak. The answer is being squeezed into a smaller and smaller corner, and physicists began to suspect it might live in the one particle that barely interacts with anything at all. There is a particle that fits the role of the missing suspect almost too well, and it earns the description by being nearly impossible to catch. It is called the neutrino, and it is the ghost of the particle world. Neutrinos are everywhere. They pour out of the sun in numbers beyond counting, and right now, as you read this, trillions of them are passing through your body every second, streaming through the earth as if it were not there. They almost never touch anything. A neutrino can pass through a wall of solid lead, a light year thick, with a fair chance of coming out the other side. They carry no electric charge, they have almost no mass, and they interact with ordinary matter so feebly that catching even a few requires detectors the size of buildings buried deep underground. For a long time, neutrinos were thought to be utterly weightless, and that seemed to be the end of their story. But then experiments found something strange. Neutrinos come in 3 types, and as they travel, they change from one type into another, shifting their identity in flight. This shape changing can only happen if neutrinos have mass, at least a little. So the discovery that they change type was also the discovery that they weigh something, however slight. And that small fact cracked the known theory open in an interesting way, because the theory, as written, had assumed they were massless. That is the first reason neutrinos draw the eye. They are already proof that the known theory is incomplete. It said they had no mass, and they do. So the framework everyone tests against is known to be wrong about this one kind of particle. And where a theory is already known to be wrong is exactly where new physics likes to hide. The second reason is deeper and stranger. The neutrino is so faint, so nearly massless, so unwilling to interact, that it might be a different kind of thing than every other particle. There is a long-standing idea that the neutrino could be its own antiparticle. For every other particle, The matter version and the antimatter version are distinct, genuine opposites. But the neutrino is so neutral, so featureless, that its matter and antimatter forms might be the same object seen two ways. No other known particle of matter can do this. The neutrino might. If that is true, it changes everything about the matter mystery. Because a particle that is its own antiparticle does not have to respect the strict bookkeeping that keeps matter and antimatter balanced. It opens a loophole in the very rule that says you can only make the two together. Through that loophole, a universe could tip toward matter in a way the ordinary particles never could. So the ghost becomes the leading suspect, not because we have caught it tipping the balance, but because it is the one particle that already breaks the theory. The one particle that might be its own opposite. And the one particle whose behavior in the early universe could have done what nothing else can. Every other suspect has been ruled out or come up too weak. The neutrino remains faint and uncaught, exactly the kind of thing that could hide an answer this large. And there is a specific story for how it might have happened. A way the lightest, faintest particle in nature could have decided that the universe would be made of something rather than nothing. Here is how the ghost might have tipped the balance, told as the leading idea and not a settled fact, because no one has caught it happening yet. Start with the neutrino's strangeness, that it might be its own antiparticle, and add one more piece. The idea proposes that in the early universe there existed a much heavier kind of neutrino, far heavier than the faint ones we see today. These heavy neutrinos would have been made in the first heat, alongside everything else, and like everything heavy in the early universe, they would not have lasted. They would have decayed, falling apart into lighter particles, and then been gone. The key is in how they decayed. Because these heavy neutrinos could be their own antiparticles, they were not bound by the strict rule that ties every other particle to its opposite. A heavy neutrino could decay into matter, or it could decay into antimatter, and here is the proposed crack. It did not do both equally. It decayed into matter just slightly more often than into antimatter. The mirror in this one process was tilted. Each heavy neutrino, falling apart, left behind a tiny surplus of matter over antimatter. One decay would mean nothing. But there were vast numbers of these heavy neutrinos in the early universe, and each one tipped the same way by the same small bias. Multiply that bias across an enormous population, and the surplus adds up. A faint preference, repeated across uncountable decays, builds into a real excess of matter where the books should have balanced. This excess would have been small, the kind of 1 in a billion that the oldest light records. And once it existed, the rest of the story plays out as we know it. The universe cools. Matter and antimatter find each other and annihilate, almost all of it down to light. But now the count is not even. There is that slight surplus of matter, born from the lopsided decay of the heavy neutrinos, and it has no antimatter left to cancel it. It survives. It becomes the stars, the planets, the matter of every living thing. In this picture, the reason the universe is not empty is that the faintest, most ghostly particle in nature had a heavy ancestor that could not keep matter and antimatter in balance when it died. The entire material world is the residue of a tilt in how those heavy neutrinos fell apart. It is an elegant idea, and it has a name in the field, and it remains the leading explanation for the matter imbalance, precisely because it fits where everything else fails. But hold on to the word proposed, because that is what it is. No one has made a heavy neutrino. They would be far too massive for any machine we can build, sitting at energies the collider cannot dream of reaching. No one has watched one decay, lopsided or otherwise. The idea hangs on properties of the ordinary neutrino that we are still struggling to measure, including the central question of whether the neutrino really is its own antiparticle. That question is being chased right now in deep underground experiments, watching for an impossibly rare radioactive event, and the answer is not yet in. So this is the shape of the best answer we have. A compelling story built on a particle we can barely detect, invoking heavier particles we cannot make, turning on a property we have not yet confirmed. The leading explanation for why you exist is a maybe, resting on a ghost, and even if it is true, it would not close the larger wound, because the matter imbalance is only one of several places where the universe refuses to be explained. Pull back from the matter mystery for a moment, and look at the whole inventory of the universe, because the missing antimatter is not the only thing unaccounted for. It is one item on a longer and more disturbing list. Add up everything we have been talking about, all the matter that survived the Great Annihilation, every star and planet and cloud of gas, every atom of every living thing, all the ordinary matter in the entire cosmos. Then ask what fraction of the universe that represents. The answer is about 5 parts in 100. Everything we have ever seen, everything our instruments are made of, everything the matter mystery is even about, is roughly 5% of what is out there. The rest is dark in 2 different ways, and we do not understand either. About a quarter of the universe is something called dark matter. It has weight, it pulls on things with gravity, and it is the reason galaxies hold together instead of flying apart as they spin. We can map where it is by watching how its gravity bends light and steers stars. But we cannot see it, we cannot touch it, and despite decades of searching with detectors built for the purpose, we have never caught a single particle of it directly. We know it is there only by its pull. What it actually is remains completely unknown. And the largest share of all, around 70 parts in 100, is stranger still. It is called dark energy, and it is not a kind of matter at all, but something woven into space itself. A pressure that pushes the universe to expand faster and faster as time goes on. We know it is there because we can measure the expansion speeding up. Beyond that, it is close to a total mystery. It is the dominant thing in the universe, the single largest component of reality, and we have almost no idea what it is. So set the ledger out plainly. The matter we understand, the matter the whole annihilation story is about, is 1/20th of the cosmos. Another quarter is matter we can feel but cannot identify. And most of everything, the great majority of the universe, is an energy we can barely describe. The part of reality that physics can explain is a thin sliver floating in an ocean of the unknown. This widens the dread in a particular way. The matter imbalance is not an isolated puzzle, a single loose thread in an otherwise finished tapestry. It is one of several enormous gaps, and they may be connected. The same new physics that tip the balance toward matter might also be tied to dark matter, or to the early moments that set the expansion in motion. The missing source of the imbalance and the missing bulk of the universe could be parts of the same larger ignorance, and it reframes how much we actually know. We have built the most precise theory in the history of science, tested it to more decimal places than almost any idea ever, and it describes a 5% corner of reality while standing silent before the other 95. The confidence of the equations, the precision of the measurements, all of it applies to the thin layer we can reach. The vast majority of what exists lies outside the theory entirely. So when the missing imbalance refuses to show up in any machine, it sits inside a much larger pattern of absence. most of the universe is already unexplained. And one more candidate for where the answer hides is a force we have never felt, acting only in places we have never been able to reach. Consider the possibility that the answer is not a particle at all, but a force, one we have never touched because it only showed itself in conditions that no longer exist. We know of 4 forces in nature. Gravity holds you to the Earth and the Earth to the Sun. The force of electricity and magnetism binds atoms together and carries every signal in your body and your devices. 2 more forces act only inside the atomic nucleus, one holding it together and one driving certain kinds of radioactive decay. These 4 are the entire toolkit, as far as we have ever measured. Every event in the universe, from a falling apple to a burning star, runs on some combination of these 4. But there is no law that says 4 is the final number. The forces we know are the ones strong enough and active enough to show up in the world we can reach. A 5th force, weaker or hidden or active only at energies far beyond our machines, could exist without ever having announced itself. And the early universe, in its first fraction of a second, was a place of energies so vast that forces dormant today might have been fully awake, shaping events in ways that left a permanent mark and then went silent. There is a deeper reason to take this seriously. Physicists have long suspected that the 4 known forces are not really separate. At high enough energy, 2 of them, electricity and magnetism, and the weak nuclear force, are known to merge into a single force, 2 faces of one thing. This has been measured. And the strong suspicion is that if you went to even higher energy, the energies of the early universe, the other forces would merge too, until all of them became aspects of a single unified force. In that first heat, there may have been only one force, which then split, as the universe cooled, into the 4 we know. If that splitting happened, it was one of the most important events in the history of everything, and it occurred at energies we cannot remotely reproduce. The moment the unified force broke apart is exactly the kind of moment that could have tipped the balance between matter and antimatter. New forces, new particles, new cracks in the mirror, all active in that instant of splitting, all leaving their mark on the matter that survived, and all of them gone or dormant by the time the universe was a second old. This is the hardest kind of suspect to chase, because it may be permanently out of reach. To make a new force active again, you would need to recreate the energies of the early universe, and those energies are so far beyond the most powerful machine ever built that the gap is not a matter of building a bigger ring. The energy where the forces are thought to unify is trillions of times higher than anything the collider can produce. To reach it directly, by the methods we know, you would need a machine larger than a solar system. So the new force, if it exists, may have done its work in a moment we can never revisit. Using physics we can never switch back on. We would be left to infer it from the faint marks it left behind. The matter imbalance among them, like reading the shape of a fire from the pattern of the ash. And that brings the whole search to its hardest and quietest conclusion. The one that explains why, after all of this, the universe stays silent. So gather the threads, because they all pull in the same direction, and the direction is not comforting. The matter imbalance is real. We are made of it, so it has to be. The known crack in the mirror is real too, measured and confirmed, and it is 10 billion times too small to explain us. The new particles that were supposed to supply the rest never appeared. The rare decays all match the old theory. The trapped antimatter falls like matter, weighs like matter, shines like matter, with no flaw anywhere in it. Every direct place the answer could hide has been checked, and the answer is not in any of them. Lay those facts side by side and a single explanation rises out of them, and it is the one most physicists now quietly hold. The missing cause is not missing because it does not exist. It is missing because it lives somewhere we cannot reach. The new physics that tip the balance sits at energies so far above our machines, or in particles so faint we can barely detect them, or in a moment of the early universe so brief and so hot that it can never be recreated, that the universe can be built entirely out of it, while leaving almost no trace we can catch. This is why everything matches. The collider keeps confirming the old theory, not because the old theory is complete, but because the part that completes it is too far away to disturb anything the collider can do. The silence is not the silence of an empty answer. It is the silence of an answer that is real and active and responsible for our existence, and sitting just beyond the edge of everything we can measure. That is a different kind of dread than not knowing. Not knowing leaves room for hope, for the next experiment, the next machine, the breakthrough around the corner. This is the growing suspicion that the corner may be unreachable, that we have found the edge of what our instruments can show us, and the thing we most need to see is on the far side of that edge, and no machine we can plausibly build will cross it. The honest summary, the one the field would give if pressed, is this: we know the imbalance happened. We have a strong candidate for how, resting on the ghostly neutrino and its heavy ancestors, but we cannot confirm it because the pieces are out of reach. And we cannot rule out that the cause is stranger still, a new force from the first instant, a layer of physics that switched off when the universe cooled and will never switch on again where we can watch. So the cause is real and hidden. That is the resting point of the whole search. Not solved, not abandoned, but cornered into a place we may never be able to follow. The universe will not tell us why it chose to exist, and it has arranged things so that the reason sits exactly where we cannot go. And yet none of this changes the one fact at the center of it. The fact that should be impossible and is not. You are here. The matter that should have cancelled did not. Whatever did the tipping, whatever the cause, the result is sitting in your chair reading this, made of the survivors of the largest act of destruction the universe has ever carried out. Go back to the beginning, to the first fraction of a second, and see it now for what it was. Not a birth in any gentle sense. A fire. The most complete act of destruction that has ever happened or ever will. In that first instant, the universe was almost pure energy, and the energy poured itself into matter and antimatter in equal floods, pair after pair, a thing and its opposite, filling all of space with twins. And then, as the heat dropped, the twins turned on each other. Every particle of matter found its antimatter partner, and they annihilated and became light. Across the entire universe, at once, matter and antimatter destroyed each other in a wave of annihilation, so total that it consumed very nearly everything that had just been made. This is the real story of where everything came from. Not creation, but survival. The universe did not build itself up, particle by particle, into the world we see. It built itself up into an almost perfect balance of matter and antimatter, and then it erased that balance back down to light, burning away nearly the entire contents of existence in the process. What we call the universe is what was left when the fire ran out of things to destroy, and the amount that was left is the number we have carried through this whole story. 1 part in a billion. For every billion particles of matter that the fire consumed, a single one survived, because it had no antimatter twin remaining to meet. The other billion became the faint glow that still fills the sky, the light of the great annihilation, the radiation of nearly everything that ever was, destroyed. So the matter that makes up the stars and the planets and the oceans and your own body is not the main event. It is the ash. It is the trace that did not burn. The one survivor in each billion. The remainder left over when the universe finished consuming itself. Every solid thing you have ever touched is a fragment that escaped the fire. Not because it was special, but because the count was off by one. And it happened to be the one without a partner to destroy it. We came very close to never being. If the balance had been just slightly more perfect, if that one extra particle in each billion had not been there, the fire would have finished its work completely. The universe would have annihilated itself down to a uniform glow of light, expanding and cooling forever, with no matter in it at all. No stars, no planets, no chemistry, no life, no one to notice the emptiness. The most likely universe, by the simplest reading of the laws, is one in which nothing survives the fire. That universe did not happen. This one did. And the difference between them, the entire reason there is something here instead of bright and silent nothing, is a flaw in a mirror that we have measured, in part, and cannot fully explain. A tilt of 1 in a billion, from a cause that hides beyond our reach, made the difference between a cosmos and an absence. You are standing inside the answer to a question the universe will not directly answer. You are the proof that the fire did not finish, and that is the strangest place to leave it, because it turns the whole story around to face you. So here is the question we start with, and here is where it lands. The laws say the universe should be empty. A bright, silent nothing, all matter cancelled by its twin, no stars, no planets, no one. By the simplest and best tested rules we have, that is the universe we should be living in. And we are not. Everything we found only made the puzzle deeper. The crack in the mirror is real and far too small. The new particles never came. The trapped antimatter is a flawless twin in every way we can measure. The best answer we have rests on a ghost we can barely detect. And the cause itself seems to hide at energies we may never reach. The universe broke its own deeper symmetry. Just barely. Just enough. And then arranged for the reason to sit beyond the edge of everything we can see. But strip all of it away, and one fact remains standing. Simple and impossible. You exist. The matter that should have been annihilated in the first second was not all of it. One part in a billion was spared, and that spared fraction became everything. It became the stars that made the heavier elements in their cores. It became the carbon and the oxygen and the iron, forged in those stars and scattered when they died. It became the planet that gathered out of that wreckage, and the water, and the first living things, and every generation since, all the way down to the cells reading these words. Think about what that means for the matter you are made of. The atoms in your hand were not made on Earth. They were made in the fire of the early universe and in the hearts of stars that died before the sun was born. They are, every one of them, survivors. They are the 1 in a billion that the great annihilation did not erase. You are not separate from this story. You are the latest place it has come to rest. The leftover, walking around, aware of itself. That is the part that should stay with you. The matter imbalance is not a distant fact about particles in a tunnel under France and Switzerland. It is the reason your heart is beating. Every breath you take is being taken by matter that won an almost impossible reprieve, that escaped a fire which consumed 1 billion times its number, for a reason no one on Earth can fully name. You are the exception the laws say should not be here. The universe came within 1 part in 1 billion of being nothing at all. It missed. And in the gap left by that miss, In that single survivor out of each billion, everything you have ever loved or feared or wondered about found its room to exist. The stars, the long climb to life, this moment of you reading the last line of this, all of it living in the margin of an era the universe should never have made. You are what the fire could not finish,